here, and I'm going to do a couple of exam questions from last year's PHY314 exam, questions 4 and 5. So question 4 says that you've got an expanding universe with a scale factor A of t that increases exponentially with time, which means that A of t has the form e to the mt. Right? And you're told that there's a bullet fired from a gun with initial proper velocity. So here's your gun, and proper velocity Vp, which is literally the velocity at which it travels away from you as you measure it with a meter stick and a stopwatch, which equals dxp by dt, and we'll call this proper velocity v0. Okay, so the direction of motion is along the x-axis and its proper velocity is constant. So this dxp by dt is a constant v0, it stays the same for all times because there's no external forces. So the first part of this question is show this universe has a constant Hubble parameter. So the definition of the Hubble parameter is the ratio of the time derivative of a, dA by dt, over a. So because a has this rather simple form, dA by dt is just m e to the mt, and a is just e to the mt. The exponentials divide out, and you get that h of t equals m, which incidentally equals h at any time, so h0 for example. So that's part A, so that was very easy, 1 mark. Okay, so part B, I have show that the co-moving coordinate of the bullet xct is given by some differential equation. Okay, so the way you do that is you say, suppose r is a vector from me to the bullet. So r can be expressed as either a co-moving distance, which I call xc, times a basis vector which is co-moving ec of some time, or it can be expressed as the proper distance times an ordinary non-expanding basis vector, which by the way isn't a function of time, it's just an ordinary basis vector. It could be a unit vector in some units. Okay, and all you do is you recognise that ec of t, the basis vector that's co-moving, is the scale factor times the proper basis vector, so that these co-moving base vectors get longer and longer with time if the universe expands, or if you've got a universe in the contracting phase, they get shorter and shorter. Okay, so you substitute that into the above equation and you get A of t times xc times ep on the left equals xp ep on the right. The EPs then appear both left and right, so they cancel, and you end up with xp equals xc times A of t. Now this bullet isn't co-moving, so it really is moving away from you. So xp is a function of time, xc is a function of time because it's not co-moving, A of t is a function of time because the universe is expanding, so all these three things are functions of time. But in particular on the left, this equation, we've got xp. Now if you do dxp by dt, you end up with this constant velocity v0, and that has to be equal to d by dt of the stuff on the right, xc, which is a function of time, times a, which is a function of time. Now because you've got a product of two terms, you have to do the product rule, and we know what the form of A of t is. A of t is just e to the mt. So this is d by dt of xc of t e to the mt. So doing the product rule on that, we get dxc by dt times e to the mt plus xcm e to the mt, and that has to equal v0, and that is the solution to part B. Okay, now the next job is to solve the equation to find an expression for xc. The way you do that is to actually go back to this form here. Because look, this form has d by dt of some function of time equals a constant. Now that's a differential equation that you know how to solve. So we write d by dt of xc of t, a of t equals v0, which means we must have xc of t times a of t equals v0 times time plus some constant we'll call big C. Maybe we shouldn't use C there, we should use D. C is after all speed of light to a of this. Which means that we have xc of t equals e to the minus mt v naught t plus d. Now we put in initial conditions, so we know that the bullet's fired from the gun at t equals 0. So xc at t equals 0 equals 0. So we have 0 equals v naught times t, which is 0, times e to the m minus mt, which is again 0, plus d, so that means that d equals 0. So we're left with the expression that xc of t equals v naught t e to the minus mt. Now what does that look like? Well, we can sketch it. At small times, e to the minus mt is dropping exponentially from 1, but it's multiplied by a function which is increasing linearly from 0. So what you get is you get this kind of behaviour, and then at large times e to the minus mt is going to dominate, so it has to go to 0. So in between there's got to be some maximum. So this is xc is a function of time. If you want to know when xc is momentarily 0, if you want to know the other time when the velocity is momentarily 0, it's here. This is dxc by dt equals 0, so it's got 0 slope. So you need to find a maximum of this thing. So at the maximum, dxc by dt is 0, which equals v0 e to the minus mt, again using the product rule, minus v0 t n e to the minus mt. You can factor out v0 e to the minus mt, and you're left with 1 minus tm. So that equals 0 when t equals 1 upon m, and that's the rest of the question. Okay, so that's question 4.